So this is a typical sine wave. This sine wave here, we see it's crossing 0 at the time t equals 0. Okay, so we're crossing 0 at time t equals 0. And so what that means is that there's going to be no phase shift. Okay, so there won't be any phase shift with that. We can see here that it's peaking at 208 volts. And so therefore the negative value would also be minus 208 volts. And we can see that it crosses 0 again at time 0.016667 seconds. Okay, so this time is in seconds as indicated down here. All right. So when we look at a sine wave, we can see the peak value of that. And so that is V peak. All right. So when we want to write the voltage of the voltage form, the equation for this sine wave, we want to write this for any time t, and the first thing we would do is write down the peak voltage. So this would be 208 volts peak. Okay, so that means the peak to peak is going from 208 to minus 208. So peak to peak is twice that, which would be 416 volts. All right, and then we can determine the frequency. Now the frequency F is given by the amount of time it takes to complete one cycle. So again, we see that it's crossing 0 at time t0. It's going up, it's coming down, it's going negative, and so now at this point it's starting to cross 0 and go positive again. So that is one complete cycle. So from this point here, and where it first crossed 0, which in this case was time t equals 0, that is the period. So we usually use a capital T. So a capital T indicates the period. Okay. And in this case, the period is 0.01666, and actually this just goes on and on in this case on there. So that is the period. So if we were going to write that period down as our answer in Blackboard, we would have to put it in 3 significant digits. So we need to shift this over here. So it would be 1,6 point, and then the next value would be a 6. But the value just to the right of that is also a 6, and so we need to round up, so that's going to be 1.67 milliseconds. So when we do our answers in Blackboard, remember that we have to put in values in 3 digits. And so we would round that up to 16.7 milliseconds. That's an S there. It didn't show up too well here. Okay, so that is the period of this waveform. Now the period states how long it takes for one complete cycle. The frequency tells us how many cycles occur in 1 second. So the frequency is 1 over the period. And so if we do 1 over the 16 milliseconds. Now remember, you want to use at least 5 digits when you do your calculations. If you use this round up version, you might actually end up with a round off error. So make sure you take your digits when you're actually doing the calculations, take them out to at least 5 digits. So the frequency now is 1 over 0.016666, and so if we calculate that, we're going to find out that that is like 60.0. Okay, so to 3 significant digits, that is 60 hertz, which of course is the standard frequency that the electric company uses here in the United States. Okay. So if we're running 60 hertz frequency, that says that every 16.7 milliseconds is going to be one complete cycle. All right, so now, when we look at this time domain function, so when we look at the time domain function of our waveform, we see omega t here. So there's our omega t. And omega is defined as being 2 pi times the frequency. So 2 pi times the frequency, or since the frequency is 1 over the period, we could also write it as 2 pi divided by the period. All right, and this is the frequency in radians per second, right? So omega gives it to us in radians per second. So when we look at how long it takes for a complete cycle of a sine wave to occur, we could look at it in 3 different units. We could look at it in time, in seconds or milliseconds, how long it's going to take for one complete cycle. That would be the period. Or we can look at it to see how many times it's going to repeat that cycle in 1 second. So, in this case, the frequency, right, this is cycles per second, or how many times it's going to complete a full cycle within a second. So it's going to do 60 complete cycles in 1 second. And then we have radians per second. Now remember that radians, when you talk about generating electricity, you have effectively, you have a coil of wire on the top and the bottom, and then you have a magnet in here. So you're rotating this magnet, and you have a north and a south pole. And so as the north pole travels through the top coil, that would give you like your maximum. When it's actually perpendicular to that would be your maximum point. And then as this rotates around, so as this magnet rotates around and the north pole comes to the bottom coil, that would be the negative piece down here. So when we are doing, so when we're looking at radians, okay, or radians per second, there what we're saying is this is how many times, this is how many revolutions we're going to have around the circle, right? So radians is talking about going around the circle. And so radians per second is how many revolutions, how many complete revolutions that this generator or a motor being driven by this is going to travel, assuming at least that we have only 2 poles in the motor. All right, so that's what radians per second. Radians per second is an indication of actually how fast the generator is spinning around to generate this. So we're going to have our sine wave. Okay, and what we put in the sine wave is got to be radians. When you calculate sine, you can do it with degrees, or you could do it with radians. But when you're talking about this here, omega t, well, omega t is defined as radians per second. And therefore, we have to multiply it times the time. So radians per second times seconds, right? Radians per second times seconds. The seconds would cancel, and we would end up with nothing but radians inside of our sine function, and we could then evaluate it. So we need to take 2 pi f, which is 60 hertz, okay, so we're going to take 60 hertz times 2 times pi. Okay, I'm using the octave software here, where pi, of course, is our irrational constant of 3.14159, so on. So it's just being rounded up to 5 digits here. But inside the computer, using the octave software, inside there, pi is actually taken out to at least 30 decimal points. All right. So, but anyhow, so when we see this, we see 376.99. All right, so if we take that out then to three digits, it would be, we would round up. So we would round this up from 376.99. We're going to round the 6 up to a 7. So we're going to have 377 times t. Okay. And so this is what we call the time domain form of this particular sine wave. So this is the time domain. We get the peak value, so we find that the peak, it's a voltage. So in this case, our unit there is voltage. And we find the time. Okay, the time gives us the period, how long it takes for one complete cycle. So we're looking for it to start crossing 0, cross 0, and then go all the way up, max out, come down, bottom out at the negative, and then come back up and then start crossing a 0 again. That is the period. And then we can calculate the radian frequency. Okay, this omega, this is lowercase Greek letter omega, so you pronounce that omega, and this is 2 pi times the frequency. And so this gives us our time domain representation of the sine wave.